All right, so today we're going to look at SO3, the matrix group SO3, and its associated algebra, written in the Gothic letters SO3. And this is typical part of the sort of a natural progression that is used throughout sort of the study of the subject, is you learn about SU2 over the complex, and you learn about SO3, which is over the reals, together for two reasons. One is that they're sufficient complexity that they represent, they are a good example of all of the basic things you need to know about Lie groups and Lie algebras. In particular, the structure constants are interesting to derive. But they're not so complex that they take hours and hours to work on. So they're kind of, you know, they're a good demonstration groups, but they have wide-ranging physical applications. These are the rotation groups in a three-dimensional vector space. The rotation group it ultimately has to do with rotations in space. And that's important because the laws of physics are invariant depending on, they don't care what orientation your vector space takes. So remember, an element of this group is going to take, in principle, it can redefine the basis of a 3 by 3 vector space, right? So you have not a 3 by 3 vector space, but a three-dimensional vector space. An element of this group can change the basis of a three-dimensional vector space, but still preserve the Euclidean metric on that space, which is exactly what we would expect anything physically reasonable to do. It's just rotating a coordinate system, but preserving this metric. And so the laws of physics will be written in some coordinate system, and all those laws of physics should be invariant under these kinds of rotations. So it shows up in physics a lot. But what's also important about these two groups is that they're related, right? And one of the relationships that's really going to be obvious after today is that they both have the same Lie algebra, right? They both have the same Lie algebra. In fact, there's another group out there called U1 of the quaternions that also shares this Lie algebra. So that's going to be able to open up our study of the question, well, what if I'm sitting in this Lie algebra and I exponentiate, you know, where do I land, right? Or do I get something that's equivalent to all these groups? Does the fact that they all have the same algebra mean that all of these three groups are isomorphic as groups? The answer is no, it does not mean that, but this is an important question that we have to study. But in order to study it, we still want to just understand these three groups well. So we're going to do that first today. So the defining condition for all of our matrix-preserving groups was that the complex transpose of a group element multiplied by the matrix that we use to represent the metric for the underlying vector space times the group element has to equal the same matrix. So this process of transformation of the metric should be invariant. We kind of went through that in large detail early on in the class. So now for SO3, the defining condition for SO3 is that G be Euclidean and that these matrices be real. So the first thing is this complex transpose part just gets turned into the regular transpose, right? We'll leave G in here. A regular transpose, I guess, has to be like a T, and then O, right, and equals G. Then we go to our infinitesimal matrix. What we're going to do is we're going to say there's some Lie algebra out there that has that will take infinitesimal matrices out of that Lie algebra, and we'll add them to the unit matrix, I, right? And these guys are elements of SO3 in the vicinity of the identity. And so what you may remember from our previous decision to sort of simplify our little pictures here, we're going to consider the group with its manifold base coordinate system, some identity element indicated here in red, and then some small neighborhood around that identity element. All of the matrices in there are understood to be the identity matrix plus some element of the Lie algebra. Now, there's been a few people who have asked some really good questions about this process, right? The process that produces these small matrices. And it's a really good question, right? Because you have this addition And the problem with this addition is that M is an element of the Lie algebra, right? And I is an element of the Lie group. M is not an element of the Lie group. And I, as we'll see soon, is not an element of the Lie algebra. But they are matrices. They're both matrices. So this addition is simple matrix addition. But it is not the matrix addition that exists in the Lie algebra, which is a vector space and has its own addition. So any two elements of the Lie algebra are closed under the vector addition of the Lie algebra. But that's not what this is, because that does not have to be a member of the Lie algebra in general. And it isn't in SO3's case. In SO2's case, it actually, there was... for briefly, remember when we considered U2, the identity was actually an element of the Lie algebra. But still, this addition is not the Lie algebra's addition. And there's no other addition in sight because the group does not have an addition property. The group operation is matrix multiplication. It's not matrix addition. So there is no matrix addition here. So this process is really part of, the way I like to think of it, is it belongs to the mapping that takes the Lie algebra, an element of the Lie algebra, into this region infinitesimally close to the identity. Now, that would only be legitimate for infinitesimal values of M, right? And we know that the Lie algebra it's an algebra, so those, it'll have a basis, x1, x2, and x3, and any element could be theta 1, x1 plus theta 2, x2 plus theta 3, x3. And these numbers can be finite, right? So you would never use those in this expression. You would only use it when these guys are infinitesimal. And the way Gilmore expresses that is he puts these little deltas in front of it to remind us that we're dealing with an infinitesimal m. Now, an alternative way of doing it is allow an arbitrary element of the Lie algebra and then slap an epsilon in there that is multiplied by it and assume the epsilon is small. We'll look at that. That would be called sort of it turns this thing into a one-dimensional subspace of the group. We'll worry about that in a moment. For example, you can exponentiate t times m, where t goes from 0 to, say, some finite value 1, for example. And now you're dealing with a one-dimensional collection of matrices in SO3. But that many books do it with this approach, with the epsilon approach. And in fact, why don't we just, for generality, why don't we just do that here? Why don't we put this little epsilon in here and say that the matrix M could be any element of the Lie algebra, but epsilon has to be infinitesimal, right? So that's what this plus is all about, right? The plus is part of the mapping. It's the rule that gets us from the Lie algebra into SO3. But that addition is matrix addition, but it doesn't exist in the group, and that addition is not the addition of the algebra. It's an addition that's the property of the mapping, right? Ultimately, it comes from the fact that this is the true mapping, and you take its derivative and you set and then you set the value of the independent variable to 0. And to first order, you end up with this expression. All right, so to proceed, though, let's just, we execute this, right? We go ahead and the transpose just moves inside the sum, and then you blow this up. I pulled the g out, and you get I epsilon m plus epsilon m transpose plus epsilon squared m transpose m. So what we say then, well, second order terms, they go away. The g's actually cancel, right? So this becomes I, right? But then that I will cancel with this, so this becomes 0, and you end up with epsilon m plus epsilon m transpose equals 0, or m plus m transpose equals 0. So this m plus m transpose equals 0, that's the defining condition for this to be true for SO3, is that this infinitesimal matrix that you would add to get a member of this group near the identity has to satisfy this condition, which is not a very difficult condition to satisfy. In fact, you can write down a matrix right away that has the property. And this is it, right? This matrix, if you transpose it, it's just like adding a negative sign. So you end up with m plus negative m equals 0. And that's the way this matrix works, because m transpose equals negative m for this matrix, So this is the way Gilmore presents the general m. But remember, he's using m as being an infinitesimal matrix, so he's got these deltas in here, right? He's got these deltas in there. Now, if you took those deltas away, you'd be all right. You would just need to include this little epsilon up front, which many books do. But we'll stick with his method for right now, these delta thetas in there. Now, why did I put theta 3 here and theta 2 here and theta 1 here? That's just convention, because we want the answer to kind of end up with matrices that are conventionally used. But you could have just put, you could put theta 1, theta 2, theta 3, and minus theta 1, minus theta 2, and minus theta 3, which would have been a little more obvious, right? Why would you put one negative sign up here and not one down there? That if you were to solve this from scratch without any preconceptions, you would have done that. You would have put the minus sign down here instead of up there, right? So, the answer ultimately would have come out equivalent or the same. So we're going to accept Gilmore's decision about how to draw this matrix. But the important thing about this is that we can now create the basis, right? If we look at this matrix right here, we can always make it by taking these three matrices and multiplying by the parameters. So these three matrices now become the basis of the vector space of Gothic SO3. So Gothic SO3 has now a basis that we will call x1, x2, and x3, where it'll end up being delta theta 1 x1 plus delta theta 2 x2 plus delta theta 3 x3, which we'll write as delta theta 1 x, or theta I xi, right? We'll use the Einstein summation. And then, once we have the basis of the Lie algebra, we're going to calculate the connection coefficients. So the connection coefficient between, the Lie bracket of x1 and x2 is this matrix product. And again, we have the same issue I think I mentioned before, right? This matrix multiplication is the matrix multiplication. Oops, what's that one doing there? Is the matrix multiplication of two members of the Lie algebra. But the Lie algebra does not know about matrix multiplication. The Lie algebra knows about bracket, but it doesn't know about matrix multiplication. This product will not be a member of the Lie algebra, or doesn't necessarily have to be a member of the Lie algebra, because it doesn't know about this. There's no requirement that the Lie algebra be closed under matrix multiplication. It must be closed under this bracket operation, but not under this. So this guy may not even be in the algebra. Therefore, this addition sign, which is actually a subtraction sign here, that may not be under the algebra either, right? Because if this isn't a member of the algebra, and if that's not a member of the algebra, then this certainly can't be an operation that's known to the algebra. So this whole process is known to the algebra as a whole, but these little parts inside, that's just standard matrix math that's known to the mapping that takes, the bilinear mapping that takes x1, the bilinear mapping that takes two members of, how would I write it? I guess I'd write it as SO3, Cartesian product SO3 to SO3, where this mapping is the Lie bracket. The Lie algebra knows about the Lie bracket, but what goes on inside this Lie bracket stays inside the Lie bracket, right? It's encapsulated in the Lie bracket, and it's just part of the mapping. So that's just an interesting thing that it's been brought up a couple times in the comments, so I wanted to make sure I mentioned it. So anyway, what is the result of this Lie bracket between x1 and x2? Well, this product is just this matrix with only one element. Notice these are highly singular sparse matrices here when we do this. That's not unusual. And this product of these two puts this together, and then we subtract this one from this one. What do we get? We get equals, something's not going to be right here. Look at, what's the value of this element? It's, this element here is this row times this column. That's -1 times -1. So this is actually a positive one, right? So this is going to be 0, -1, 0, 1, 0, 0, 0, 0, 0, right? Which equals minus x3. So we already have, right off the bat, we have x1, comma, x2 equals minus x3. And I won't work it out, but you can calculate x2, x3 is going to be minus x1, x3, x1 is going to be minus x2, and you know that these are going to be the opposite of flipping them, right? Because flipping them, just all that does is takes this matrix here, takes this guy here and puts it over here, and this guy here and puts it over here. So it just switches things around the minus sign. So this will be minus x 3x2, and ultimately we have the rule xi xj is minus epsilon, it's going to equal minus epsilon I j k x k, right? That's going to be the rule for, that's going to be the commutation rule. So that means that C I j k, which equals which is defined through this commutator, right? So so now we know that C I j k is going to equal minus epsilon I j k, just like this. Okay, so that's showing that the two Lie algebras, the one we did last week and this one, are actually the same. Now we got to remember that the special in special 03 means the determinant equals to 1. So we have to check the determinant of one of these infinitesimal matrices must also equal 1. So this sum here is explicitly written here, and now we just calculate this determinant. Oops, in the middle of this I'm missing a minus sign there. I just put that back in. And you end up with this expression, 1, and then you have the product of these three deltas minus the product of the three deltas, which would be rejected for two reasons. First, it's third order, right? So that's a problem, but they cancel out perfectly, so it doesn't even matter. And then these are rejected because they are second order, so you end up with 1. So the determinant of this is 1, which is kind of interesting because when we did this process for SU2, remember that we actually ended up with 4 basis vectors, and the possibility of having a determinant that wasn't equal to 1 made us eliminate one of the basis vectors, right? So this naturally falls into SO3. The S part just comes for free in this particular case. We'll have a look at why. We'll compare SO3's derivation with SU2's again later regarding this point of the difference between SO3 and O3, right? And same with SU2 and U2, right? So what have we got so far? Well, we've got our group, we've got our algebra. The reason we have our algebra is we figured out the 3 basis vectors to the algebra as a vector space, and we've discovered the structure constants. And so that's pretty much the whole story for the algebra. And we understand that the mapping from this algebra into the infinitesimal region around the identity is I plus, I guess we went with epsilon m, where m is any element of SO3, of scripty SO3, right? So as long as we have a small epsilon. So we can now map from basically any point here into any point right around the identity. So just as we did with SO2, the question is wait a minute, we want to get we want to get throughout the entire group, right? There's this other map we need, right? The exponential map, which we'll write as exponential, and I'll just put y, where y is some element of SO3, right? I guess we should write y is theta I xi, right? So y comes out of SO3, goes to the exponential map, and then the exponential map takes it into some element of SO3. I keep having to say SO3. It means the group or the algebra, right? So I guess I should say Gothic SO3, or just from the algebra to the group, is what I mean, I suppose. So now what we want to be able to do is we want to be able to calculate what is this matrix. As a matrix, what is that thing? What is this element? What is this element? What is this element? What are these elements? And we want to calculate each one of these elements in this group. So we fully understand how to calculate any element in this group given its coordinate. And so that's our plan. We're going to do that calculation. Now, last time we did it for SU2, so we know how this kind of thing is done. We're going to put together matrices, sum them together using the definition of the exponential, like this. I mean, we're going to do the same thing. We're going to take a different approach. Gilmore likes to do a different approach for Gothic SO3 than he did for Gothic SU2. And so and I never miss a chance to review something elementary, right? If you're doing a complex problem in advanced physics and you end up having to integrate something that you used to know how to integrate when you studied Calculus 2, well, now's the time to review it, because I'm sure you've forgotten, right? Nobody remembers every integration technique that they learned in Calculus 2. So we're going to learn a little thing about linear algebra, or relearn something about linear algebra that will make this calculation much more interesting and simple for calculating these matrix elements. So let's begin that. So we're going to begin with the basic matrix. This matrix represents some element of the Lie algebra, right? It's a finite element of the Lie algebra, but it's an arbitrary element of the Lie algebra. So what we're going to do is we're going to calculate the determinant of this matrix. And so the way we'll do this is we take the diagonal elements, right, if we remember how this worked, and we add in, I always added in minus lambda to do the calculation. And then you take the determinant of this matrix after you subtract off this diagonal element, right? Whatever would, in this case it's easy. It's just put minus lambdas because they're all zero. But if there were diagonal terms, it would be whatever the diagonal term was minus lambda. But you're going to produce the determinant of this guy, and that will be the characteristic equation when you set it to 0. I keep forgetting to put my minus signs down here on this guy, right? None of it makes sense unless you have that minus sign. So let's see, we end up with this characteristic equation, right? We have minus lambda cubed, and then these guys are all positive. These guys are 3 negatives, so you get the negative. So those cancel, just like before. I don't see why it would be any different. And then this way you get a minus sign for everything, but this minus sign will cancel, so you get lambda theta 2 squared, lambda theta 3 squared, and then theta 1 squared, like this, right? So now what do we do? Well, we set this equal to, we set this equal to 0, right? And that'll be the characteristic equation. We pull out a lambda, and so we get lambda cubed and minus, so we get this lambda out front and then all these minus signs in here. So what are we going to do? Well, we'll get rid of the minus signs and make them plus signs by just dividing everything by -1. And then we'll also combine these guys into a single term, which we'll just call lambda squared, right? That should be familiar actually from our last lecture, how the sum of the squares of the 3 parameters became a thing. Now the problem here is that, right, this is a superscript. And I want it to be a superscript because I've chosen to subscript I wanted the subscript to be on the basis elements of the algebra, so you need a superscript to get the summation. But now I'm running into this notation problem, right? I want to square things with superscript, so I need to add parentheses. And when I'm done, I want to just say, okay, I'm going to call this thing theta squared, but that looks a lot like theta 2. Ugh, so I'm not quite sure what I'm going to do. Let me think about it. Well, I guess the first thing I'm going to do is fix this cube, which should really be a square, right? And then I'll go lambda, we'll take out the -1, I'll go lambda squared plus theta squared equals 0. And it turns out I don't need the theta squared for long, right? So I'll put it in red so we know it's a square, and then we'll break this out to lambda, lambda, and then it's theta plus, or lambda plus I theta, lambda minus I theta equals 0. And so now we know what our eigenvalues are, right? The eigenvalues are going to be I theta and minus I theta and 0. But it turns out what we really want is this form here. Oh, I am going to need that theta squared, darn it. So this form here gives us lambda cubed plus theta squared lambda equals 0, right? And this is the secular equation. Gilmore calls it the secular equation, which is sort of old school. We call it the characteristic equation if you studied this thing anywhere after, I don't know, 1960 or something. I don't know when the change happened, but this is what we've always called it in all the linear algebra books that are somewhat modern. It's the characteristic equation. So this is the characteristic equation of this matrix here, right? So this matrix has its associated characteristic equation. The thing that is worth that we want to review is the Caley-Hamilton theory. And the Caley-Hamilton theory says that the matrix, the underlying matrix, for whom this is the characteristic equation, actually satisfies its own characteristic equation. So the matrix that created this, if I cube that matrix and I add theta squared times that matrix, it's going to equal 0, right? So that's actually pretty important, because our matrix we're going to call theta I xi. So theta I xi cubed equals theta squared theta I xi, right? Or wait a minute, equals minus that. So this guy right here is what we're going to use as our tool to solve for the exponential that we're working on. We're going to take advantage of this little tool. So notice the way the notation goes. This is not theta 2. This is theta squared. All of the individual thetas are never going to show up again except in these sums. So there shouldn't be any confusion. But this guy here, theta 2, I better write it down. Theta 2 is defined as theta 1 squared plus theta 2 squared plus theta 3 squared. So this is really theta squared. I shouldn't call it theta 2 squared. This is not theta 2. This is theta squared, and that one is theta 2. All right. I'm forgiven because, well, Gilmore does something similar. He would just pull this to the denominator. He would just pull this down, right? Because it doesn't matter whether this is really up or down, except when we use it in the Einstein sum. So Gilmore actually throws it on the downside of things eventually. But regardless, we understand this now as theta squared, and it equals the sum of the squares of the different parameters. All right, so we start our process here. I wrote down our rule that every third power of theta I xi can be replaced with a first power multiplied by this constant. So I'm going to write down the rule for the exponential, and you can kind of see how this is going to apply. This is an infinite sum, but the infinite sum is finite. Each term is going to be some product of third powers, and each time we see a product of third powers, we can replace it with this. And if we see 3 products of third powers, we're going to get 3 of these, which is another product of which is going to be another third power, which we replace again. So we're going to be able to cast out third powers, and that's the strategy here to execute this entire infinite sum. Very clever, and we'll do it step by step, but this is where we start, and then I'm going to blow this up into even and odd terms. So this is the odd terms when n equals 0. This is for n equals 0. When n equals 0, this is 1. This is 1, so that would be the first power term. When n equals 2, this becomes, when n equals 0, this becomes 1, and that becomes 1. When n equals 1, this becomes 3 factorial, third power. So it's always going to be the odd terms. And then I'll do the even terms in blue. We took out the first even term, the n equals 0 term here. I already pulled out. It's the identity matrix. Remember, this is a matrix, right? It's the sum of 3 matrices, so that's a matrix. That is matrix exponentiation, which is just the product of the matrix with itself this many times. This is a real number here. This is a matrix, right? So n equals 0, this is the first even power other than 0. So this is the second power, and then the denominator is the second power. So this is all the even terms in blue. So let's first study the odd terms. Now we're going to exploit this we're going to cast out cubes, matrix cubes this way. So let's first study this term here. All right, so I've tried to work this out, right? So this expression is the odd terms, right? So the first of the odd terms is this linear term, and there's nothing you can do there. But the second of the odd terms is this cube term, and that cube can be replaced by our formula, right? This formula right here. So we replace any cube term with minus theta squared theta I xi. So we end up with this expression right here. So we have minus theta squared over 3 factorial theta I xi. The n equals 3 term starts out, or the n equals 2 terms gives us the fifth order term of the expansion, which is the third odd term. And I take that fifth power, I break into a third power and a second power. The third power gets replaced using our formula with the same minus theta squared theta I xi, but I have this square term left over. So when those combine, they give me another cube, which takes out another minus theta squared. So I now get theta to the fourth, because the minus signs cancel, and I'm still left with the linear term. So you'll notice every odd term is basically just the linear term so far times an increasing factor of theta. So fun fact. Let's see if it's persistent, right? And sure enough, the seventh power term is the sixth power term times a linear term. The sixth power term comes out with 2 of these versions of the formula, which is minus theta squared, leaving behind theta I xi squared, right? That's the application of this formula times itself, basically. And then I have this linear term here, but that forms another cube, which adds in yet another minus theta squared, which gives us our negative sign back, and the linear term. So we always get the linear term, and then we get increasing powers of theta, each going up by 2, and then alternating minus signs. So that's going to be the pattern. So it looks like we get an expression that looks like this to match our pattern, right? The minus sign is there for every odd value of n. So we have this minus 1 at the n up there. Then we have this 2n plus 1 factorial. We have theta to the 2n in all of these spots, right? 2, 4, 6. And then we have always this matrix tagging on at the end as a factor. Now the important part is this matrix is not raised to any power at all. In fact, the summation, which is n equals 0 to infinity, doesn't affect this this term at all. So that actually can come out front. It's just a multiplicative factor over the entire sum. So we can distribute that guy out. But we do want, in order for this to look like the sine series, which is kind of what we're after, we do want this to be a 2n plus 1. Otherwise, it won't match the sine series. So we have to multiply by a factor of theta. So in that case, we have to divide by a factor of theta. And when we do that, let's see if I got this right. So theta comes out here. This factor comes out, right? This is just a constant in front, but this is a division by the whole thing. So this becomes like something you modify. We're going to turn this into the normalized coordinate, right? Because that's the individual coordinate, and this is the square root of the sum of the squares of the coordinate. So we'll call that the normalized coordinate. This is the matrix now. The matrix is totally out front. So this is just a number. And of course, we recognize this as the straight up sine theta series. So our final answer is, and so we end up with this expression here, right? So this term here, this term gives us this. So I can actually substitute that right back here, and I guess I'll do it in green. It's going to be the identity matrix plus the normalized coordinate xi sine theta, right? And the normalized coordinate, right, is like it's this over the square root of theta 1 squared plus theta 2 squared plus theta 3 squared, right? That's what we mean by x1 hat, right? Okay, so look how good this is, right? We took our exponential, we broke down the obvious straight up definition, you know, there it is, definition of a summation, and then we broke the summation into this even and odd parts, and then we used this fact to start casting out cubes, which forced everything to be a linear term. So we're obviously going to do exactly the same thing here, and we're going to end up with some kind of cosine series, right? Because what's going to happen is, notice that if I had the matrix squared, I couldn't use this at all. This will not help me with square powers of our matrix, right? It only casts out cubes, and well, in principle, it could complexify. It could make more difficult linear terms, right? We could replace linear terms with cubes, but who would do that? We can cast out cubes, but we can't cast out squares. So squares are going to be left behind in this term, and but that should all be evens, and there's going to be some kind of cosine thing going on. So let's have a look at that. All right, so in this case, I'll just leave this out there. I don't think I made any errors here, right? Here's the first term of the series, which is the even power. Can't do anything to that because like I said, our expression here does not deal with the squares. Then the n equals 1 term, you can see n equals 1 will be 4 factorial, 4 in the exponent. 4 breaks down to a factor into a cube plus a linear term. The cube gets replaced using our Caley-Hamilton theorem. This is, in case I didn't say it, this principle here is the Caley-Hamilton principle, the principle that a matrix, the Caley-Hamilton theorem says that a matrix satisfies its own characteristic equation. But using our Caley-Hamilton substitution, we end up with this. These two combine and form another square, and you end up with a minus sign coming from the 1 Caley-Hamilton replacement. For n equals 2, this happens, you get x to the 6th, that's cube, that's 2 Caley-Hamiltons, or one Caley-Hamilton replacement squared, which is this guy squared, which the minus sign goes away, you get theta to the 4th, and then you get the square of the matrix. You can't get rid of that. And of course, now we're seeing that what's left over are matrix even powers of the matrix instead of linear powers. And then when n equals 3, you end up with an odd powered, the negative of theta to the 6 over 8 factorial, and then of course you have the square. So we can now sum this guy up. So let's remind ourselves that the cosine sequence is ultimately 1 minus 1/2 theta squared plus 1 over 4 factorial theta to the 4th, etc. So we do have some problems, right? Because our eta equals 0 term first of all, our eta equals 0 term doesn't give us 1, right? Our eta equals 0 term gives us a positive 1/2 theta squared, right? So that's one problem with this guy. I'm looking at this guy now. And our n equals 1 term gives us a minus theta squared over 4 factorial, which is well, first of all, this gives us a theta to the 0. Our expression, okay, all right, our expression for n equals 0 is a theta equals 0 here, and the wrong sign. So it's the wrong power and the wrong sign. And our n equals 1 term, which is our second term, it's got the 1 over 4 factorial, but it's coordinated with the wrong sign and, again, a power 2 too low. Well, we know how to deal with the power of 2, or the even powered exponents being low by a factor of 2. We just multiply the front of our guy by, I'll do it in red, 1 over theta squared, and then we add the plus 2 there. So that takes care of the powers of 2. So now we don't have this term, so we're missing that term. But at least we got the sign, and the sign of this is wrong still, right? So that's a problem. But we fixed the exponents, right? So the exponents are now 4 and 6, right? So we're okay with that. But the signs are all wrong. So what do? Well, what do we have? Well, we have, ultimately, this is going to be plus 1/2 theta squared minus 1 over 4 factorial theta to the 4th. So ultimately, if we look at it, we've got 1 minus the real cosine theory, right? So if we looked at 1 minus the cosine series, we would end up with a 1 minus here, and we would end up with a 1 minus a negative 1/2, which is plus 1/2 theta to the 4th minus 1 over 4 factorial theta to the 6th, etc. And that would actually match our sequence. So our series is 1 minus cosine theta, and then we have these factors in front. So our final result is going to be, right, so this is our final result, right? This front part is this normalized piece. You bring this square term inside the square of this brackets, and you normalize the parameter, so you get the normalized parameter sum. So this is a matrix, the square of this matrix, and then this guy that's left behind, everything is equal to 1 minus the cosine of theta. And so that's our expression. Now I'll go back to here and I'll add it in blue, plus theta hat I xi squared 1 minus cosine theta. And this now, that is a matrix, right? This is a matrix here, right? It's a matrix sum. This is a matrix sum squared. This is a number, and this is a number. So you give me theta, I calculate the matrix, right? So if you give me theta 1, theta 2, and theta 3. I use that, I calculate theta, which is easy. It's just the sum of the squares of those things. And then I calculate theta, theta I xi, which is a matrix, right? And then I calculate theta I xi squared, which is that same matrix squared, right? Which is another matrix, right? And then I take this matrix, put it right here, take this matrix, put it right here, calculate 1 minus cosine theta, calculate sine of theta, because I've calculated theta, add these two matrices together, add it to the identity, and that is a guaranteed finite element of SO3. Phew, so what would that actually look like? Well, let's do it. So let's just look at this term first, right? You just blow it up, and you're going to see that in the final matrix, you're going to have a theta hat 1, 1 sine theta in the 2, 3 position. So I can go over here to the 2, 3 position, and I can write theta hat 1 sine theta, right? And likewise, it's obviously going to be the case that I will have the opposite of that here in the 3, 2 position, right? So there's going to be a minus theta hat 1 sine theta here. And then I can do this, I can do the same logic to these guys right there. And that takes care of this term right here. So now let's calculate the blue term. So I have to calculate this thing, right? I have to calculate the sum of these guys. I'm going to add these cats up and then just square the matrix, right? That's ultimately the answer. So that's not too tough to do. Let's just muscle through it. So I guess the first thing I'll do is I'll just recombine them into the standard matrix. I always screw up the signs. Let me make sure I got it right. Yeah, the minus sign here. So now I just square that thing to get this guy squared. All right, I think this is what I get. Let me double check it. This first one is 0, 0 times 0. Then it's 3 times, it's theta 3. So it's minus theta 3 cubed, and then it's minus 2 cubed, right? So now here I've taken the indices and I've moved them into the subscript so I can square things easily. So that's why I've changed from superscript indices identifying the parameters to subscripts, right? So here all the superscripts are just squares which appear in the diagonal. This guy here is this row times this column, so it's 0 times 0 plus 0, then it's minus times minus, so it's a plus, theta 2, theta 1, theta 1, theta 2. Then it's this row times this column, it's 0, 3 times 1 positive, comes in as a positive, and then 0. And then I'll just check this bottom one is this row times this column, which is 0, 1, 3 as a positive, like that. And then boom, sorry, it's this row times this column, and this row times this column is 2, 3, oops, there should be a little hat here, 2, 3, 2, 3, and then 0 and 0. That's what this is. It's always a positive. So these cross terms are always positive. And then the 3, 3 example should be this times this, which is minus second power of 2 minus the second power of 1, which is the way we have it. Okay, so this is the result of that matrix. So now we have to take that creature and multiply by 1 minus cosine theta, where this is a number. This is the number 1, right? So, but that is going to now inform us on the other elements of this thing. So, for example, we got to go back to this. This part here contributes a matrix. We just calculated what this matrix contribution is. The 1, 1 element of that matrix contribution is going to be this times 1 minus cosine theta. So I could go, whoops, where do I go? I go here, and I would write minus theta 3 hat squared minus theta 2 hat squared times 1 minus cosine theta, like that. And now I can fill in this whole thing with the cosine theta part. Okay, and if I didn't rush it too fast, I should have gotten it all in there. All right, so then, but we're not quite done because there were 3 parts to this, right? There was this part, which we've just put in there, but there's also this part here, this 1 part. So what do we have? And I think, is it 1 minus or 1 plus? It's 1 plus, huh? Okay, so we have to do a, now remember, each of these is a number, right? This whole thing is the matrix, but each matrix element is a number. So yeah, so I can go 1 plus, and then it's 1 plus, and then it's 1 plus right along the diagonal. And the reason that that's important is because, well, this is, first of all, we're done, right? This is the answer. And so you give me theta 1, theta 1, theta 2, and theta 3. I'll calculate these normalized values because I calculate theta, which is the sum of those squares. I calculate cosine theta, I calculate sine theta, I calculate the normalized values. Then I start calculating these, this is implied addition, right? Everything's added together. Then I add everything together and I end up with these matrix elements, right? So this is it. This is the answer. Now, it's not exactly the answer that you see in Gilmore because what he notes is that 1 minus theta 3 hat squared minus theta 2 hat squared equals theta 1 hat squared, right? That's the definition of the way these things are normalized. If you look at the definition of theta and respect to theta I, you'll realize that when you sum up those squares this way, they normalize to 1, right? So you end up with this. So the point being is that if you would blow this up in this first term, these two come out, add to the 1, and then just give you the one that's missing in positive form. And then you have the cosine part is left behind, but it's just 1 times the cosine part. So just to put a fine point on it, 1 plus this term, right, which is what we're dealing with on all of the diagonals, right? The only difference is a permutation of 3, 2, 3, 1, 1, 2, right? 1 plus this term is equal to 1 minus cosine theta plus that term plus cosine theta. So I'm adding and subtracting a cosine theta. Now I factor out a 1 minus cosine theta, and I get 1 minus cosine theta is times 1 minus theta 3 hat squared minus theta 2 hat squared plus cosine theta. But this just equals theta 1 hat squared by the way these things are normalized. And so your final result is cosine theta plus theta 1 hat squared times 1 minus cosine theta. And this is the form that Gilmore uses. So I could go back here and make that replacement right here. This becomes, oops, let me just get back into the regular thickness of my pen. So it's 1, oops, let's see, it's cosine, let me fit it into the box. So it's cosine theta plus theta 1 hat hat 1 minus cosine theta. That's what belongs there. And likewise on all the other diagonals. Okay, and that gives us the final matrix that's in Gilmore. So this is it, right? This is how you parameterize. This is an element. This is an arbitrary element of SO3. We've done it. We've exponentiated the algebra, and we've got this answer. So that's kind of cool. All right, so that's where we'll stop for today. So now we understand, let's see, what did we understand? What we were able to do is using the properties of SO3, we were able to derive the basis elements of Gothic SO3, the Lie algebra, and we devised the structure constants, although we didn't really use the structure constants for this next step. The next step was knowing the properties of SO3 is different than knowing how to tell me every single matrix in SO3. But once I knew the algebra, I was able to exponentiate, using this exponentiation to get any element of SO3, even if it's a finite element, some arbitrary distance away from the origin. It's easy to get anything close to the origin. You just follow this prescription by adding an infinitesimal element of the algebra to the identity, and then you're right around the origin. But to get somewhere far away, you have to multiply these things over and over and over again to get there, and that's this exponential. And we executed this exponentiation, which is defined through this Taylor series. We took the definition of the Taylor series itself and executed the exponentiation. We broke into its even and odd terms. We used the Caley-Hamilton theory to help us cast out cubic terms of the matrix, which was fun. And we ended up with this expression. It had the sine and the cosine piece. The cosine piece showed up in a little weird form. We got 1 minus cosine in there. But once we looked at this, we said, all right, there's our matrix. There's our square matrix. We calculated the matrix and the square matrix, and ultimately we got this. And this is a number. Remember, you give me parameter theta 1, theta 2, theta 3. I calculate theta, right, which is going to be the square root of the sums of the squares. Then I calculate these hats, And once I have these hats, these are just numbers, right? And you just crank out and you get a number right there. You get a number right there. And this ends up being a 3 by 3 matrix. Okay, so that's all for this. And next lesson, we'll actually look at the quaternion version of this. So we'll have all three in hand. We'll have SU2, SO3, and U1, and then we can start talking about some of the cool elements of the group theory here. All right, see you next time.